Okay, yeah, we're recording now. So, complexity and TOC, slightly different to how we want to lay things out compared to DSA. But basically, how you want to, things you got to know, basically, first, are some of the summations they gave us on the slides. They won't give us these summation formula because we're not actually getting a formula booklet. So, just make sure you remember those. Yeah, if you want to just screenshot now, you can. Otherwise, yeah, I'm just going to move on to this bit. Okay. So there are three kinds of complexity, which the three different notations that we need to know according to the the topic list that they gave us. So worst case complexity gives us the upper bound, and it's given by Big O. That's what we know already. Best case complexity gives us the lower bound. It's given by omega notation, and average case gives us the expected cost of a random input if we were to give. So not worst case, not best case, any input we can give. That's what average case would kind of be like. What's the most likely complexity? And that's with theta notation. Here you can see like a graph, and the dots represent like different inputs. So you can see like it's very rare to get the worst case. However, it's important because when we're designing systems, we need to know what is like the what we need to know a guarantee basically. We need to know in what time is my program guaranteed to give an output. So that's why we use worst case. And average case is quite useful for deciding like which algorithms to use for what like problem. So you want to use the one normally with like the best average case because that means on average it'll perform the best. Because it's in the industry it's quite unlikely that you're ever going to get like a worst case input. Okay, cool. So with all those defined, we need to know in terms of like this one's in terms of time rather than complexity, but it basically like is analogous, right? It kind of represents the same thing. So here's a program written in Java. So what it does is it takes an input, which is a list of characters, and basically it waits 1 second. Then, if like the ith character has a for loop, it goes through the characters. If the character it's currently on is an A, it will elapse 1 second, so wait 1 second. If it's not an A, it will basically wait 2 seconds. And then after that for loop ends, meaning it's gone through all the characters, it'll just wait one more second before terminating. So the set of characters that we can take in for this program is A, B, and C. So what we're kind of asked to do is work out the worst case and average case for like in terms of time for this problem here. So in order to do this, we need to consider well, worst case is pretty easy. Let's go through worst case first. The worst case, can anyone tell me what is like the worst like going through one of these like a single character, right? Going through one of those, what is going to be like how much time can you take if the say for length one, if we're just going through a single character, what is the maximum time that the program can take? Four, right? Other important thing to note is that when we have long inputs like this in this question specifically, we're gonna do it time based on a specific length of input. On the elapse in the for loop should be indented one the right on the last line. Uh, this one that should be indented there. Okay. Um, cool. Okay. All right. And basically, so the worst case, as Shay said, would be 4 seconds because for a single length one input, you would the worst case would be it's not an A, and you would run it for 1 second, run here for 2 seconds, and then run for 1 second here. So it would give you complexity of four. Now, the average case, um, explain what would have happened if this wasn't indented. It would be outside the for loop. So wait, it would run the same. As in, but yeah, just so it doesn't look confusing. Okay, it was just for aesthetic purposes. Okay, cool, great. Anyways, so yeah, the average case, you need to consider the probability, and that's what's important here. So you may remember from like maths, we looked at expected values. So the expected value is the probability times the value, right? So in this case, the values we're dealing with is time in seconds. So to work out the expected value, what we do is we sum all of the possible outputs multiplied by their corresponding probabilities. That's an important formula you should probably like remember. You sum the all the outputs get multiplied by their probability of occurring. An important assumption that we're making here is that the input has a uniform chance of being either A, B, or C. So all three characters have an equal chance of being chosen. Provided that's the case, then um, there are two possible outputs, like two possible times this can take. It can either take 4 seconds, which is what we would get if the character was a B or a C, or it can take 3 seconds, which is what we'd get if the character was an A, because you only wait 1 second here. So the probability of each character, as you can see, is 1/3, uniform distribution. But once we multiply the probability by the time, we can see that the probability of it running in 4 seconds is 2/3, because B and C both cause it to run in 4 seconds, whereas only A causes it to run in 3 seconds. So the probability of it running in 3 seconds is 1/3. The probability of it running in 4 seconds is 2/3. Therefore, when we add these up together, so I've just kind of like, this can be like rewritten as, probably would be better if I did it as like 2 multiplied by 4, kind of. That would kind of show it. So I've multiplied the probabilities basically by the value that the probability is for, and then summed all of those up. So here it's just basically 4 times 2/3 and 3 times 1/3, which gives us this. So that is how you'd work out the average case in this example. Does that make sense? Can we do complexity for Turing machines? Yep, that's what we're about to move on to. So yeah, that's just levels of detail in complexity. So this was all the stuff about Polly, Constance, Big Tim, and Little Tim. But I don't think we need to know those guys. So let's just move on. Okay, right. This is the important stuff, right? So this is what you guys are probably looking for proving complexities. Um, so if you want to prove the big O time complexity of a program, you need to first get its headline complexity. So there's a bunch of different cases in which things can happen. So I have a question here where, okay, may I ask why you made the time complexity into a mixed fraction? Just for aesthetics. Yeah, you're right. Yeah. So I wrote it as a mixed fraction. So like I could, you could kind of see like how many seconds it takes. Like it's more easy to visualize that on a number line than 11/3, for example. So yeah, that's the only reason. You can write it as whatever you want. Basically here, so if you have the complexity, this is like the exact the exact number of seconds taken to run the program. When it returns false, that was from the actual previous part of the problem, but we're not going to look at that part right now. So basically, when a program runs, we're going to assume it takes 9n to the 5 plus 3n squared plus 1 seconds to run, where n is the size of the input as normal. So what we need to do is we need to say, does the program have a time complexity of n to the 4, or does it have a time complexity of n to the 5 or n to the 6? And we need to justify our answer. So there's like a set proof that you can do, and I'll just remember how to do the proof, like the format. It's quite intuitive. So here we're solving A. So we're trying to prove that we're trying to prove that does the algorithm have a complexity of n to the 4? Obviously, we can see that it doesn't because the dominant term is n to the 5, but we need to prove that. So that's what we're going to do here by justifying the answer. So the way we would need to do that in TOC is slightly different from how we do it in DSA. So in TOC, we'd say there exists C and there exists N0. So these two terms basically must exist, and we'll define the rest of it later. But these two, if they exist, both of them, that means it runs in the complexity what we're trying to prove it for. So what are the conditions? So for all n greater than n0, so this is kind of like a minimum value of n, and that's because that big O is notation is for big values of n. It may not necessarily always, it doesn't need to hold for like small values of n. It can like not hold for small values of n, but as long as quote unquote when n tends to infinity or gets really big, the complexity is always higher and acts as an upper bound of the actual number of processes being done. That's what we're trying to look for in big O notation. It does not need to be like exactly um, for all the values of n. So it's only for all the values of n greater than a certain minimum amount. So if n is greater than that, it would work basically. And then c is a constant that we're going to apply. And this is because when we look at big O notation, we discard the constant, right? So when say the complexity of something is 3n squared, we write that as n squared. So we can't say that it would definitely be less than n to the 4, but we can say it would be less than some constant times n to the 4, which we assume that we removed when we got it down to m to the 4. So in this case, if this is all true, if all of this can be satisfied, then T of n is in O of n to the 4. So that is the outcome. It's kind of like this being all true implies that. Okay, so how do we do that? So there are two types, two different methods basically. There is one for disproving and one for proving. Currently, we're trying to disprove because we know it's not going to be n to the 4 because the dominant term is an n to the 5 term. So how do we disprove? Well, we write it out like this. This is the equation from above here. I've just written it out again. And then I've set the limit of n to infinity. And what I did was I divided all of the terms by the complexity we're trying to disprove it for. So n to the 4, I divided all of the terms by n to the 4, which left me with 9n plus 3n to the minus 2 plus n to the minus 4 is less than or equal to c by itself. Now, as we now do limit n to infinity, because remember, we only care about complexity when n reaches big values. We don't care what it is for small values. So when we do that, we can see that 9n tends to infinity as n tends to infinity. And these two, because the exponent is negative, they both tend to 0 as n tends to infinity. So what we're left with is infinity is less than c. And that's a contradiction. Therefore, we've disproved it because infinity cannot be less than any constant. I hope that makes sense. So there is no constant that's bigger than infinity. So no value of c that can satisfy this statement above. Because remember, this statement above would imply that it runs in O of n to the 4, but we've just disproven it. We've shown a contradiction that there is no valid value of c because you can't have a constant that's bigger than infinity. So this bit's false, and therefore, like, we can say this bit's not going to be true. So yeah, that's kind of how we would disprove. Hoping that makes sense. Let's get on to proving then. So that was disproving. Now, this is how you'd prove it. So now we're going to see, we're doing part B now. Does Page's program have a time complexity of O of n to the 5? Justify your answer. So again, same process, writing everything the same out, but we're just going to change this bit here. Instead of doing to infinity, we're just going to get values. So we need a value of c and a value of n0 such that all n is bigger than n0 and 9n to the 5 plus 3n squared plus 1 is less than or equal to some constant multiplied by n to the 5. And everything means the same thing as what we did above. Like constant is just the constant that we omitted because we don't care about constants when we go to big O. And n0 is the minimum value of n, where this formula would become viable or true. And if this is true, then we'd say that it's the machine, the Turing machine or the algorithm, it runs in O of n to the 5. So instead of doing n to infinity, and I'll tell you what the problem with that is later, you can do it. You can do it in exactly the same method that we did above, but it is more difficult when you can do it in a much easier way as we've done it here. So when n is equal to 1, you can do it to any value, but 1 is normally the easiest, least maths done. So you just set n is equal to 1. Then you just do, where you work out the value of c when n is equal to 1. So c is equal to 9 plus 3 plus 1. Um, that's how we work out c basically. It's just going to be like um, subbing in a value for n and then working out what c could be. So that's 13 in this case. Then um, 9n to the 5 plus 3n squared plus 1 is less than or equal to 13n to the 5. And, and then you can see here that, okay, question. So it would be like, yeah, exactly. So, yep, as you can see, when we subbed 1 into here, it's just 9 multiplied by 1 plus 3 multiplied by 1 plus 1 is less than or equal to c multiplied by 1. And that's why I do it normally sub in 1. You can sub in any number, but 1 just means you don't really have to worry about what the power is. It's just going to be 1. So c we get is c is equal to 9 plus 3 plus 1 is equal to 13. And then now with that value of c, uh, yeah, 1 makes most sense to use. So there are actually some cases where they'll tell you a value and you can't use 1, but we'll get to that later. So basically, now what we can do is just sub in the value of c back into our original equation. So 9n to the 5 plus 3n squared plus 1 is less than or equal to 13, which was the value of c, n to the 5. And if you look at this equation, as long as n is greater than or equal to 1, it's always going to be true. This expression, this side of the function, which is the actual number of seconds the machine is going to take, is always going to be less than this bound here. What's our value for m? M. What do you mean by m? What's m? N0 is m. Okay. I mean, yeah, I mean, you can write N0 as m. It's just a variable at the end of the day. I don't think it matters what you write. Yeah, if you want to call it m, call it m. It's just a variable at the end of the day. It doesn't really matter what you write it as. As long as you keep it consistent throughout the proof, it's fine. So, okay, what's going on? Ooh, what have you done, Shay? Everything to the highest power. That's why we do. Okay, I think Shay's got that one. Yeah, okay. So anyways, we have 9n to the 5 plus 3n squared plus 1 is less than or equal to 13n to the 5. And you'll notice that this holds for every single value of n that's greater than 1. And therefore, you have now satisfied this, that you have found a value of c and you found a value of n0, or m if you want to call it m. You found a value for these two. So you can say thus we can have c is equal to 13 and n0 is equal to 1, meaning that the Turing machine or like algorithm is in O of n to the 5 complexity. And yeah, that's how you'd prove that something is that complexity. Last part of the question was, does Page's program have time complexity O of n to the 6? And the answer is yes, it also has complexity of n to the 6 because we've proven it to have complexity of O of n to the 5, simply because n to the 6 grows faster than n to the 5. So if we've shown it as an upper bound with n to the 5, n to the 6 will definitely also be an upper bound. And yeah, that's kind of it. So there are two methods. Remember, disproving is with infinity. Proving it with is just you find values. You don't need to do the infinity stuff. You can just find two values that satisfy the the condition at the top. If you've done that, you've shown that it is in that complexity class. Yeah, that's pretty much it. I don't have anything else. No, the rest is on Turing machines. Yeah, that's complexity for you. I see in the bottom it says there has to be a value of m and n there. Took n zero and then okay wait. Oh, value of yeah, typo. It's not supposed to be m and n zero. It's supposed to be c and n zero. So that should be c over here. I think I may have been looking at the handout or like yeah, c. There needs to be a value of c and yeah. Does that yeah, yeah, exactly, Danny. I made a typo there. So that's C and then zero. If you if you guys want to call it, I didn't realize that we were gonna call this M, but yeah, it doesn't matter. It's a variable at the end of the day. You can call it what you want. I found it useful calling it N0 because I think that's how we learned it in DSA or like somewhere. I don't know. Some tutorial guy told me. But any questions? Can you use reasoning that both functions are increasing and that one overtakes the other? Uh, you know what? I think that's like um I don't know how exhaustive you yeah, as in that's basically what we're showing here with this infinity one. Um we're basically saying that you can't have a large value of n where this would work, meaning it's overtaken it when it gets really big. If you write just that it overtakes it in words, I don't know if you'd get all the marks. So it could be, yeah. So the complexity of this program is just O of n to the anything greater than or equal to 5. Yeah, that's correct. Yes. You don't have to do any like polynomial solving here. So that's the advantage. There's no polynomial solving at all. You can just prove it without doing polynomials. The one where you would have to do polynomial solving is this type, when you try and prove for lim n is to infinity, and this is why you wouldn't use it, because, yeah, if you want to just look at this, you'd have to then work out a value of n, which is not really needed because it's never asking you for the strictest bound. It's just asking you for the bound. So you can just use this method and give any value of c and n that work, and you're sorted. C and n0, sorry. What is Because what if the at n0 is equal to 1, the upper bound is not larger than the function? Then you just say n0 equals 2, I guess. If is it gonna be is it gonna be But the thing is, it because you've subbed in 1 at the start, it's always going to be um greater than or equal to 1. For like if you work out c basically, this method basically ensures that this is always true because if you sub in n is equal to 1 at the start and then you work out c based on that, then it's you kind of making sure that the constant you're using holds for all the values of n greater than 1 because you subbed in 1 here. So yeah, that's why you wouldn't really have to worry about it not being um, true for 1 exactly. If you use this method, if you use like a different method, that does not always hold up. Um, any more questions, or are we solid? I'm not seeing anyone typing, so yeah, that's complexity. I'm gonna hand back over to Shay then. Shay, come back, come back. Yeah, cool.
What's up?
Was
Awesome. Okay.